Okay, sorry for the interruption. So we continue with a phase plot. Okay, so this is our phase plot for each terms here. So we need to draw our final phase plot. Okay, so our starting point here is at minus 90. Okay, so for the next part here, okay, notice that we have a slope of positive 45 degree per decade, 0, 0. So that means for this region, it has 45 degree per decade slope. So that means if we start with minus 90 plus 45, it should intersect with the minus 45 degree here. Okay. So for the second part, we have slope of positive 45 plus slope positive 45 plus 0 plus 0. So that means for the second region, our slope gonna be positive 90 degree per decade. So that means our intersection will be at 45 degree here because negative 45 for this line to have slope of 90 degree per decade, it will intersect with 45 degree here because 45 plus 45 becomes 90 degree per decade. Okay, so that is our third point here. Okay, for the third region, we have a slope of positive 45, negative 45, 0, 0. So for the third region here, it will have slope of 0 degree, meaning that straight line here. So our next point is similar with the previous one. Okay, so for the next part, we have slope of 0 and then we have negative 45. So for the fourth part, it will have slope of negative 45. So let's say this point is 45. 1 decade after, it should intersect with 0 so that it will have slope of 45 negative 45 degree per decade. Okay, so after that it's a straight line, so just make it a straight line here. Okay, connect the dots, you will get something like this. Okay, for the final phase plot for this transfer function. Okay, so we have another example. Construct the Bode plot of the system with transfer function gs equals to 200 s plus 10 divided by s plus 1 s plus 100. Okay, convert to standard form first. Okay, so this is our standard form. And then determine the frequency range and corner frequency. So our corner frequency here is 1, 10, 1, 100. So we get our corner frequency 1, 10, 100. Okay, so this here you can just ignore, this is a typo. Okay, so frequency range is 1 decade before the lowest and 1 decade after the highest corner frequency. So it's gonna be 0.1 until 1000. Okay, this is just a you could say mathematical calculation from transfer function to get your standard form. Okay, so this is our final standard form g j omega. So this is our constant 20. So we convert in dB, we get 26 dB. Okay, so see the yellow line here. This is representing our constant at 26 dB. Now we will look at 0 at origin. Okay, j omega here. So corner frequency here is 1. Okay, remember for 0 at origin, at corner frequency must intersect with 0 dB. So this is one point here. So 0, it has positive slope 20 dB per decade. So that means 1 decade before it will intersect with minus 20. 1 decade after it will intersect with 20 dB. So it has 20 dB per decade slope and so on. Okay, for the second term, 0, which is corner frequency at 10. Okay, remember for 0, that is not at origin, start at 0 until intersect with corner frequency, which is at 10. Then it will goes up with the positive slope, which is 20 dB per decade. So that means at frequency 100, it will intersect at 20 dB. At frequency 1000, it will intersect with 40 dB. So this line will has 20 dB per decade slope. Okay, so we complete with the 0 terms. Now we look at the pole term. First, we look at this pole terms here, which is corner frequency at 1. Okay, notice that the line start with 0 dB until intersect with the corner frequency 1, and then it goes down with the slope of negative 20 dB per decade. That's why 1 decade after, which is 10, intersect with minus 20. 1 decade after, intersect with minus 40. 1 decade after, intersect with minus 60. Okay, for the last term of poles here, our corner frequency is 100. So start 0 until it intersects with corner frequency, which is 100, and then it goes down with the slope of minus 20 dB per decade, meaning that at 1000 frequency, it will intersect with minus 20. So we have 5 lines here, so we gonna need to add all of this line to get our final magnitude plot. Okay, so our starting point here, we have line constant at 26 dB, and then here red line, green line at 0 dB plus minus 20. So that means 26 plus minus 20, it become 6. Okay, so this is 6 dB. So second point, so for this part, it has slope of 0, 0, positive 20. So this, for the first part, it will has positive slope with 20 dB per decade. So that means if we start at 6 plus 20, point here gonna be 26 dB. Okay, for the second region, we have 0 plus 20, 0, negative 20. So total the slope become 0. So that's why next point is similar with the previous one, which is at 26 dB. Okay, so for the third part, we have slope positive 20, 0, positive 20, 0, negative 20. Okay, sum all this line, we get slope of positive 20 dB per decade. So that means 26 plus 20, it become 46 for this intersection here. Okay, for the next part, we have slope of positive 20 plus positive 20 become 40, 0, maintain 40, minus 20 becomes slope of 20, minus 20 become 0 for the slope for this part. 0 dB slope. So that means this is our point here for this part. Okay, so the rest is similar because here is positive 20, positive 20, 0, negative 20, negative 20. So this is our final magnitude plot for this form or transfer function. Okay, for the phase plot for constant 20, which is 0 degree, and then for the 0 at origin here, phase plot is 90 degree, straight line at 90 degree. And then for this 0 term here, corner frequency 10 must intersect with 45 degree here. So 1 decade before it becomes 0, 1 decade after it becomes 90, and after that it's straight line here. Before this, straight line at 0 degree. Okay, now we will look at poles at corner frequency 1. So for poles, the phase plot is slope of negative 45 degree per decade. Intersect at corner frequency 1 here, it should intersect with minus 45. 1 decade before, intersect with 0. 1 decade after, intersect with minus 90. And after that, straight line. So our last terms for pole, which is corner frequency at 10 here, at 100, must intersect with negative 45 degree. So 1 decade before, intersect with 0. 1 decade after, intersect with minus 90. And after that, straight line. Before frequency 10, straight line at 0 degree. So now we have our phase plot for 5 terms here. In this graph, there's no plot for constant, but you know that for constant it has a line here at 0 degree. Okay, so our starting point is 90 plus 0, 0, 0. So our starting point is 90. Okay, so look at this part. It has slope of 0, 0 and negative 45. So that's mean 90 minus 45. Our next point be at here, 45. Okay, so for this part, positive 45 minus 45. So the slope becomes 0. That's why for the next point is remain at 45. Okay, for this region, it has positive slope 45, negative slope 45. So maintain at 0 slope. So 45. This one here, our slope is 0 minus 45. So slope here become minus 45. For 45 minus 45, it will intersect with 0 at this intersection. Okay, so after that, just a straight line. So that is our final phase plot for this transfer function. Okay, this is the Bode plot if you use MATLAB. Okay, so now we move into stability. To determine the stability, we need to check gain margin and phase margin. Okay, so the formula for gain margin is minus LM. LM is for our magnitude plot that we get from the Bode plot based on gain crossover frequency, and our phase margin formula 180 plus value of the frequency that we get at the phase crossover frequency. Okay, so the system is stable if both gain margin and phase margin is positive or more than 0. Okay, so how to determine the gain margin and phase margin? Okay, first, to find gain margin here, this is gain margin, you need to look at the phase plot. Okay, so this is our phase plot, our final phase plot. Okay, let's say this is our final phase plot. To determine gain margin here, you must find the intersection phase plot with minus 180 degree. Okay, so this is the intersection of phase plot with minus 180 degree. So this frequency here we call gain crossover frequency. Okay, for example, here is 100. So you look at the magnitude plot here at 100 frequency. Okay, find the intersection with the with the magnitude plot here at 100 frequency. For example, this here is the intersection. Or if you draw magnitude plot is above and phase plot is right below with the same frequency, you can just go up and then find the intersection here. Okay, this region here what we call gain margin. This point here that you will get the value from this scala here is our LM. Okay. Okay, so to find phase plot, you have to look at the magnitude plot. Okay, so this is magnitude plot. Okay, so to find phase crossover frequency, magnitude plot has to cross or intersect with 0 dB. For this case, this is the intersection of 0 dB and magnitude plot. So goes down, find the intersection at the phase plot. Okay, so this region here what we call phase margin. Okay, so value here is our phase value. Okay, so we will look into this example. Okay, so we need to determine the system stability from this Bode plot. Okay, first we want to find gain margin. Okay, what's the first step to find gain margin? We look at the phase plot. Okay, here is the final phase plot. Okay, so how to find gain margin? Okay, phase plot must intersect with minus 180 degrees. So this is the point where phase plot intersect with minus 180 degree. Okay, so frequency here 36.3. Or you can just go up until it intersect with the magnitude plot. Okay, so because you are using MATLAB, you can straight away read the value here, which is minus 29.5. Okay, remember here, this is value LM, not gain margin just yet. This is value of LM. Okay, so I might explain once again because this is like explain for the phase margin first. Okay, so uh, okay, let me goes back and explain once again. First, based on this slide, we want to find phase margin first. So to find phase margin, we need to look at the magnitude plot. Okay, so this is magnitude plot. Okay, so to find phase margin, find the intersection of magnitude plot with 0 dB. So this is the intersection. Okay, so the frequency is 4.51. You can read it here or just go straight down. So this is the intersection. So this is what we call phase crossover frequency, which is 4.51 radian per second. So this is the intersection. So this is the phase that we get, which is minus 117. Okay, so this is not our phase margin just yet. Remember the formula, 180 plus value that we get here. Okay, so this is value of phase that we get. This is the value for magnitude that we get. Okay, here is minus 29.5. Here is minus 117. Okay, so remember gain margin equals to minus LM. So gain margin minus LM. LM is minus 29.5. So we get our gain margin is 29.5. Okay, so to find phase margin here, just use the formula. 180 plus value here is minus 117. So you get 63. Okay, so remember to say the system is stable, both GM and phase margin must be more than 0. So in this case, both are positive value. So we could say this system is stable. Okay, so we have a second example. Okay, this is to find the phase margin first. To find the phase margin first, you need to look at the magnitude plot, which is must intersect with 0 dB. So in this case, this is our phase crossover frequency, which is 44.7 radian per second, goes down until intersect with the phase plot around here, which is value is minus 253. Okay, so this is the value that we get. Okay, so to find gain margin, you need to look at the phase plot. Here is our phase plot intersect with minus 180. So this is the point that intersect with minus 180, and the gain crossover frequency is 236 radian per second. You can just go up at the same frequency and intersect with the magnitude plot here at minus 20.8. So this is our gain margin. This is our phase margin. Okay, so gain margin is minus LM. Our LM here is minus 20.8. So we get gain margin a positive value, which is 20.8. Okay, here our phase value here is minus 253. So the formula to find phase margin is 180 plus minus 253. So we get answer minus 73. So this is our phase margin. So notice that our phase margin is negative number. So it does not meet with our requirement. Therefore, the system is unstable. For stability, gain margin must be more than 0. Phase margin also must be more than 0. If either one does not meet, the system is unstable. Okay, this is the example that you can go through and do it. I prefer for you to do it by yourself first without refer to the slide, even though the slide has a step-by-step calculation. but I prefer for you to do it by yourself first and check with this schema. And if anything that you did not understand or you get different answer, you can discuss with your lecturers. Okay, so please try by yourself first, and you can check your answer whether similar with the slides or not. And also we have exercise. Please do it, this exercise, so that you will understand more about this topic. And for the answer, you can discuss with your lecturer. Okay, that's all. That's the end of the chapter 5. Thank you for paying attention for this video, and sorry if there is any inconvenience of this video. Okay, thank you. Assalamualaikum and have a good day.